All right, so this video is going to be a hybridization of the atomic orbitals to form bonding hybrids. All right, so to explain why we talk about this, if carbon has 4 valence electrons, and let's just look at CH4, so that would be what this would look like, and it would be a tetrahedral, and so the bond angles here would be 109.5, and we know that carbon has a 2s and then has a 2p outer orbital, and that would be involved in bonding. And so if we look at that, it doesn't really add up, because then carbon would have these big round s orbitals that would be involved in bonding, and then would have these long p orbitals, and so some of them would be shorter than others. And that's not what we see. We see that the bond length of all of these carbon to hydrogen bonds is the same length. And so something has to be happening to the atom carbon that has this electron configuration to the carbon that gets involved in bonds and makes these different bonds with other atoms. And this happens to all atoms. And it's just a simpler way of viewing molecular orbital theory, which we don't get into in AP chemistry. So when I look at what happens, okay, I'm going to take those s electrons, so this is 2s and then 2p, and it normally looks like this, and I'm going to just promote one of these electrons to the 2p orbital to explain what's happening. So I have one electron in each one, and the first type of hybrid orbital that we're going to look at is called sp3. And basically what that means is that we're going to take one s orbital and we're going to take 3 p orbitals, and we're going to take them together and put them in a pot together and mesh them up so that we end up getting some hybrid orbitals, which would be 1s and 3 p orbitals. So if I have 4 atomic orbitals, then that means I'm going to get out 4 hybrid orbitals, and they would be all sp3. So when we look at that, we have one s, which is a spherical shape, and then we have the 3 p's, px, py, and pz, and we're going to mush them all together and make a hybrid out of it. And so these hybrid orbitals, we make 4 of them. These would be the 4 sp3 hybrid orbitals. And when we put it all together, we get this. And so we would see here that the bond length that all 4 of those make would be the exact same in shape, and they make these balloon-like shapes where they would then be able to go to electrostatically balanced positions where the bond angle between all of those would be roughly the same, about 109.5. All right, so let's look at some examples, and you're not going to have to draw any of this in this way. You're only going to have to be able to look at carbon and determine if it's going to be sp3 or sp2 or whatever. All right, so all tetrahedral geometries will be sp3 hybridized and have that bond angle of 109.5. So when we look at it, this would be for CH4. In flat, we draw it like this, where it looks like it's 90 degrees, but it's not, because it's not flat. So this is from the carbon sp3 hybrid orbital. And then the hydrogen isn't going to hybridize because it's just got one s, so it doesn't have anything to hybridize with. And so its 1s orbital from hydrogen will overlap with the end of the sp3 hybridized orbital and form something called a sigma bond. So a sigma bond is any bond formed by hybrid orbitals or atomic orbital end-to-end overlap. So we could say, okay, well, here's an sp3 and here's an sp3. And so as long as it's overlapping end to end, that would be a sigma bond. So any single bond will always be a sigma bond. All right, so we have one sigma bond here, one sigma bond here, here, and here to form that tetrahedron electron geometry. So when I want to check to see what the hybridization is around carbon, it's kind of like counting. You just go S, P1, P2, P3. And so that would be sp3 hybridized, and that's all you're going to have to do on the test. So it's just counting the number of bonds around carbon. You're more counting the steric number, so you'll see when I get to the examples here at the end. All right, so sp2 hybrid orbitals. So in sp2 hybrid orbitals, we're still going to look at carbon, and I'm still going to promote one of the electrons to the 2p. But in sp2, that means we have one s and two p orbitals. So that would make, since we have 3 atomic orbitals there, 1 2s and 2 2p's, we would make 3 sp2 hybrid orbitals. And so we've got 1 s and 2 p's, and we mix them together and we get 3 sp2 hybrid orbitals. And so when we look at that, we get a 120-degree angle because they're going to go as far apart away from each other as they possibly can, and that would make that flat trigonal planar shape. But what happens to this leftover electron in the 2p? So let's take a look at the next slide to see. All trigonal planar electron geometries will be sp2 hybridized with a bond angle of 120. So right here we're looking at this molecule that we've seen a couple of times in these videos. And around this carbon here, we can count. This would be 1 because it's steric numbers we're counting, not formal charge where we're looking at electrons, we're counting steric numbers. So this would be S, P1, P2. And so this carbon would be sp2 hybridized. These are the hybrid orbitals that carbon made. 1, 2, 3. So S, P1, P2. Now this is that leftover P. Okay, so these make the hybrid orbitals, 2 P's, 1, 2, and then 1 S. And so we have this thing that's left unhybridized. So that's that p orbital that's more elongated. And oxygen also has this p left unhybridized. And so a pi bond forms. And a pi bond is when unhybridized p orbitals, that's why it's called pi, overlap side by side in the same plane. So they have to be pointed in the same direction, and they actually overlap like this, but they can't draw it like that because then everything would be too close together. And so we just draw it like this and say, okay, there's overlap here. Now you're not going to have to draw it, but I want you to understand that that orbital is still there. It doesn't just disappear. And that's where that double bond comes from. So anytime you see a double bond in something, the first bond is a sigma bond. So that would be this. That would be the first bond of the double bond. And then the second bond is always going to be the pi bond. So when we look at this little bitty molecule here, I can say, okay, this is going to have 3 sigma bonds because it's got 1, 2, 3. And then the second bond of the double bond, this one, will be a pi bond. So it would have 1 pi bond. And that pi bond is made by the overlapping side by side the p orbitals. All right, and then the last hybridization that we have to look at is sp hybrid orbitals. So again, I'm going to look at carbon. So carbon has the 2s and the 2p, and there's 1 electron in each. And so this time, since it's sp, that means we're going to take the s and one of the p's, and we're going to hybridize it together. And since we have 2 atomic orbitals, we're going to get 2 hybridized orbitals. And each one would have an electron in it to be able to bond. Okay, so then there's 2 of these left over, right? Left over. And so here we have an s orbital and a p orbital, and then we mush it together, and we end up getting these 2 mushed together hybridized orbitals. And so these are always going to be linear and 180-degree bond angle because it's going to be a straight line because they're going to get as far apart from each other as possible. And so it says all linear electron geometries will be sp hybridized with a bond angle of 180 degrees. All right. So if I look at CO2 and I'm counting, then I know that this would be S and then P. So carbon here would be sp hybridized. Remember, you're counting steric number. You're counting the different areas of electron density around an atom to look at the hybridization. And so this right here is just showing the hybrid orbitals. So it's 180 degrees apart. And this would be a sigma bond because it's overlapping end to end. And then if we look here, they've left the p orbitals in this one. They took the p orbitals out of this top one so that you could just see the hybridized orbitals. But in this one, we still have the p orbitals. So there's 2 p orbitals. One is here for that carbon, and then the other one is hidden in the back and in the front. So in this one, this front one that you can see all of almost, all right, will overlap side by side with this one because they're in the same plane. And so that would be 1 pi bond. And then the back one here would overlap with this one because they're in the same plane. So that would be the second pi bond. In CO2, there are 2 sigma bonds. One is here and one is here. And then there are 2 pi bonds. One is here and one is here. So the first bond of a double bond will always be a single bond. And the second bond of a double bond will always be a pi bond. If we look at this molecule, and I wanted to count the sigma bonds and the pi bonds, the number of sigma bonds would be 1, that's a sigma, 2, 3. And so there would be 3 sigma bonds, and then these 2 would be pi bonds. So the first bond of a multiple bond is always a sigma bond. And then the last 2 of a triple bond would be pi bonds. All right, and if I wanted to see the hybridization of this carbon, well, it would just be sp, because it's linear. So it's sp. And not only that, but if you just count the number of electron domains and assign it s, p1, p2, p3 along that, in that order, you'll get the right hybridization. All right, so I drew some really big molecules here. So the first one here on the left is caffeine. And we want to determine the number of sigma and pi bonds in the molecule, as well as the hybridization of all marked carbon atoms. So I didn't mark any carbon atoms yet, but I'm going to go ahead and do that. So, all right, so if I'm going to count the number of sigma bonds, I know that this was reduced to CH3 to save space. So when I look at that CH3, I know that there's 3 sigma bonds here. So I'm going to count that. There's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So there's 25 sigma bonds in caffeine. So it's all the single bonds and the first bond of a multiple bond. And then I'm going to go back in and I'm going to count the number of second bonds, so double bonds. So there would be 1, 2, 3, 4. So that means that there are 4 pi bonds in that molecule. And then to do the hybridization, the first one around this first carbon right here, I would just go S, P1, P2. And so this carbon is sp2 hybridized. So you're just counting the electron domains around the carbon. Okay, and then if I do this one, it would be S, P1, P2. So it would be trigonal planar because all sp2s are trigonal planar and vice versa. And then it would have a 120-degree bond angle. And then this nitrogen down here, if we're going to do the hybridization, remember that that nitrogen has that lone pair there, and you can count that in the hybridization. So that would be S, because it's a steric number, P1, P2, P3. So that'd be sp3 hybridized, and so that would be tetrahedral. All right, so then on THC, all right, so let's do those 4. And first I'm going to count the number of sigma bonds. So I'm looking for all the single bonds. So I've got CH3, so there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56. I think I got them all. I might have missed some. I hope not. So there's 56 sigma bonds. And then I'm going to go back through and look for bonds that I didn't cross off. So those would be second bonds in a double bond. So there'd be 1, 2, 3, 4. That's it. So there's 4 pi bonds. All right, and then I want to look at the hybridization of the marked carbon atoms. So in here, for that carbon, it's going to be S, P1, P2, P3. And so that would be a tetrahedral. And then down here, we have S, P1, P2, P3. We're just counting the number of electron domains. So on this carbon, it would be S, because the whole double bond counts as 1. S, P1, P2. And then on this carbon, be S, P1, P2. And it doesn't matter where you start around that. You just make sure you cover all of them. The same with sigma bonds, pi bonds, all this stuff. So these sp2 are trigonal planar. It's 120 degrees. So that's pretty much it. Probably work some more in class, because I know that this can be confusing, but you're really just counting. Don't overcomplicate it. You don't have to know how those hybrid orbitals are made. You don't have to know any of that. I just like to explain it because I have a lot of students that need to know the whys. And so those are the whys.